Welcome back to the module Quality Considerations in 3D Printing. And now we will learn about the various quality control measures that we can take in 3D printing. So, moving forward, the first measure that we need to take as a quality control measure is design validation. So, what you need to do is you need to validate your design. Now, this design validation means also validating your design data. There are multiple aspects of it, such as you validating your features, you validating your tolerances, you validating your STL file, and you validating your minimum dimensions, critical dimensions. For example, in a 3D printing process, you can print only 0.3 mm and you have a feature of 0.1 mm in your design. So definitely that design cannot be printed. So this design validation is a very important process that needs to be done during your designing process itself, so that you can make design the right part for the right 3D printing process. Then we talk about in situ process monitoring or in process monitoring. So basically what you want to do is, I told you that temperature can be one of the reasons for generating most of the defects. So when you are doing a 3D printing process, you need to monitor all the important parameters, and you also need to make some coupons and specimens to validate your printing process. So basically, when you are making a part and you don't want to destroy the part, but still you want to do the tensile testing of the part or stress rupture testing, that we will study in detail what kind of testing can be done, destructive testing. So in order to do any kind of destructive testing, you need the coupons or the test specimens belonging or corresponding to that particular destructive testing to be built with the build. This is one way of doing in situ monitoring, and the other way is to monitor all the specific process parameters. And sometimes this in situ process monitoring or in process monitoring can also be done by using image analysis or a video analysis during the printing of component itself. Then the third part of it is when the printing is done, which is post-process inspection. Now, this is basically just like any other engineering process where you want to analyze or inspect the component that you have manufactured through that engineering process. In this case, it happens to be a 3D printing process. That can be measurement of critical features, dimension measurements, or that can be 3D scanning. You actually want to 3D scan the whole part. We will discuss in this module what is 3D scanning. And through 3D scanning, basically you are not only trying to measure the critical dimensions, but you generate the replica of a component in the CAD environment and then overlap with the CAD model and check how much deviations you have got. Now all the organic surfaces which cannot be measured through vernier caliper or micrometer, there we need to go for 3D scanning. Then there is non-destructive testing. So as I told you, during in situ process monitoring, we need to build some coupons for destructive testing. But once you have made the part, you can actually take the part through a series of non-destructive processes or very basic non-destructive process such as X-ray. And then you can actually check whether you have some porosity or cracks inside the part. So there are other methods of also of non-destructive testing which can be taken into consideration. But first you need to analyze your end application. What is your end application? And based on that, you decide what kind of destructive testing you need to go for, non-destructive testing you need to go for. And you also need to analyze your features, what kind of features you are having in the component. If it is organic features, you can do it through measurement using vernier caliper. If it is inorganic features, or I would say a more biomimic feature, then you need to go for 3D scan. So let's talk in detail about design validation. What do we need to consider in design validation? So before printing, you have to check the design, because you might have some errors, inconsistencies, or some compatibility issues with the chosen material. And in order to do this, you need to be clear with your 3D printing method. That is why we have learned all the 3D printing techniques so much in detail in the previous modules. So you need to know which 3D printing process you are going to use and which material you are going to use in that 3D printing process. And based on that, you have to validate your design. Now, there are some 4 or 5 kinds of validations that you need to perform. First is your geometric validation and STL file validation. So you need to check what is my minimum feature size, what is the wall thickness I'm trying to print, and if my STL file is having any error. There are certain errors that you get in an STL file, and if your STL file is having those errors, then the same errors will be replicated in your printing process, and your print might fail also sometimes. Or even if the print doesn't fail, when you take the part out, you will not be able to use that part for the end application for which you had designed and printed the part. Then there is checking of dimension and tolerances. Now, for example, if you want to print a particular part with 0.1 mm tolerance, and you choose a 3D printing technology which gives you the tolerance of 0.2 mm, 0.3 mm, which is the case with most of the 3D printing technologies, then there is no use of doing it. Or if you want to achieve some tolerances which is 0.05, no 3D printing can produce that 0.05 tolerance. So you need to consider some post-process technique which you need to account for in the design phase itself. So checking the dimension and tolerances are very critical. For example, if you want to make a hole of 0.1 mm, which cannot be made in any 3D printing process. So you need to go back and check if you can make a 0.3 mm hole or 0.4 mm hole, or you don't need to make the hole at all. Later on, you need to develop that hole in any post-processing operation. Then once you have done that, you need to validate the functionality and performance. Functionality validation is done by the FE analysis of the part in your conventional simulation software such as ANSYS Workbench. And then performance has to be validated there as well. Also, you can do simulation for the particular 3D printing process, that if I take this part to this 3D printing process, what are the problems that can be encountered? There are multiple softwares available now, such as Simufact Additive, Fusion 360, Materialize Magics, which enable the user to actually simulate the component for that particular manufacturing process. Then, yeah, this is what we were talking about, simulate printing and assembly. Now, for example, if you have an assembly feature in your part, and you have, it's a movable, two movable parts are printed together, and in order to achieve that movability, you need to have 0.1 mm gap. Then you need to check whether 0.1 mm gap will be produced in the printing process or not. So these are the basic design validation techniques that we need to do. I will just give you an example of geometric validation, which is like fixing the STL file before 3D printing. So if you see in this file, there are multiple shells, there are holes, there are floating angles. These are the some of the basic defects that we get in the STL file. Now, if these defects are still there in your STL file while you have taken up for printing, your printing will fail. So what you need to do is, what you see on your right hand side, this is a screenshot from Materialize Magics, where you get a fix wizard which detects all the problems in your file, and then you can manually or automatically using the software algorithm fix it. Now, when we talk about dimensions and tolerances, uh, every 3D printing process has got a different kind of dimension and tolerance. For example, multi-jet fusion, which is MJF process, it has got a tolerance of plus minus 0.3%. So basically, for 100 mm length, you are getting plus minus 0.2 mm tolerance. Then, what is the size, maximum size that your 3D printer can accommodate? So in case of multi-jet fusion, it is 380 mm, 284 into 380. So this much big part you can make. Now, in case if you're designing a bigger part, you have to split and plan the printing accordingly. So this is a part made in MGF. Then we talk about selective laser sintering. In selective laser sintering, again, we see that similar tolerances can be achieved around plus minus 0.3%, but it is slightly higher side when we talk about tolerance for SLS. We get for 100 mm, we get plus minus 0.3 tolerance, which is a bilateral tolerance. Then the maximum parts that can be made in SLS is around 340 into 340 into 605. This is one of the SLS part where you see that threads cannot be made properly, so they have used a copper insert which has been added in the part after printing. Then we have stereolithography, SLA, that we have studied as well. In SLA, you get the best possible tolerances amongst all the polymer 3D printing process, which is plus minus 0.2%. So it results into plus minus 0.2 mm for 100 mm. And the sizes that you can print in SLA are really big. There are really big SLA 3D printers available in the market. You can print up to 736 into 635 into 533 mm. Similar tolerances are there for FDM. It is very much similar to SLS. The parts that you can print are much bigger in FDM technology. It goes up to 914 into 610 into 914. So this is quite a large part. Then you have DMLS. In DMLS, which is basically a metal, you have slightly better tolerances than other processes. You can also get a good accuracy of plus minus 0.1 for 100 mm tolerance. And then parts can up to 400 into 400 into 400 can be printed here. Then in polyjet, you can get tolerance as good as 0.05 mm, which is 50 microns for a 100 mm part, because polyjet is a very precise technology. So when I was saying you need to check for your 3D printing method and your design tolerances. Now, for example, if you have to print a part in 0.05 in polymer, then you will not go for SLA, you will go for polyjet. Now, the parts that can be printed in polyjet currently are up to the size of 490 mm into 391 into 200 mm. Now, let's talk about in situ monitoring. Basically, in situ monitoring is monitoring of all the process parameters using different kind of sensors. Now, one new thing that has come in the market is using cameras to analyze your parts when the printing process is going on. Now, there are certain things that you can detect very accurately. Then there are certain aspects that has medium detectability, and there are certain aspects that has low detectability. For example, you can easily detect a lack of fusion. You can easily detect if there is high amount of spatter generation in selective laser melting. Now, this camera technique is largely used in laser powder bed fusion of metals, because those equipments are very expensive equipments, and even metal parts are expensive parts. So similarly, you can check for porosity, but it's the amount of porosity that you can detect is slightly on the lower side. Then you can check for the stress induced crack. Again, that comes, it's not necessary that you will be able to detect all the cracks. Then delamination. But now there are certain softwares or certain imaging methods with which you can also detect problems such as if there is anything wrong with the chemical composition, if there is anything wrong with the microstructure, or if there is any contamination in the part. So all these things can be detected. Their degree of detection may vary. So, but you can go on Google, and you can check in situ monitoring, and you can get a whole lot of data. This is a new research area in situ monitoring, but the basic aspect of in situ monitoring is that you want to monitor all the process parameters which contribute to the quality of the part while printing. So thank you, and we will meet in the next module where we will learn about the dimensional inspection of component and some techniques of destructive and non-destructive testing. Thank you.